All right, so we've talked about Newton's first two laws. We went through free body diagrams, and so now we're going to put some application to how to use these laws. Okay, so we're going to start with the idea of equilibrium. Now, if you've never heard the term, so basically equilibrium talks about everything being balanced. Okay, in terms of forces, we're talking that all forces are balanced. Okay, so how this applies in terms of our variables and what we're studying is that means that the net force equals 0. Okay, so to reiterate, net force means total. So F net means total forces, and really what we can probably more accurately see that as is when we say net force, what we're actually referring to, when we say net force, we're actually referring to if it's not equal to 0, or even if it is, think of net force as any remaining forces. So remaining unbalanced forces. Okay, so in this case, we said F net is 0. That means there are no remaining unbalanced forces. Everything was balanced. Everything canceled out with something else. But if net force did equal a number, that meant this is how much force is remaining after all the summations of stuff. Okay, so when we're doing F net, equilibrium, we are specifically speaking to the point where net force is 0. Okay, so let's put a few little application ideas to that. So if I've got a force, say, acting on an object to the right of 10 newtons, and an unknown force acting to the left, but the net force here is 0, then what is the value of the unknown? Well, a net force would mean we want to add up all of our forces here. So you've got 10 newtons plus the unknown is equal to 0. So if we solve it for the unknown, subtract the 10 over, we get minus 10 newtons. Now, that probably seems very easy, and it's supposed to, because that's exactly what it is. If it's 10 newtons to the right, how much has to pull to the left to completely balance this out? The answer would be negative 10. It's 10 newtons, and it's negative because it's got to go the other way. So that's the main idea of what equilibrium means. Okay, so let's put a few more ideas on that. So let's say we have an object. So let's say I've got a rope, and there's an object hanging from it. Now, whatever this mass is, we'll just say that we know that it's pulling down because of the mass and because of Earth's gravitational pull on it. There's a net pull down of, we'll say, 10 newtons. Right? And the object's not going anywhere. So the question would be, what is the force of tension that's pulling up on the box such that nothing is moving? So we do the same kind of trick. In this case, you've got tension, okay, and then we're trying to find total force. So, and again, because in equilibrium, net force has to be 0. So if we're doing the net, tension plus a negative 10 newtons gives us 0. So the tension must be 10 newtons. Okay, and so that's the idea of equilibrium. It's a very, very simple idea. Okay, now let's put a little more application to this. Let's say that we have an object. So we've got something on the floor. Okay, and we want to push on this object. Now, chances are the object's smaller than you are, so you're not going to push with a straight horizontal force, but rather you're going to push somewhat down on the box. And if, let's say, we push it down such that it makes a 30-degree angle with the horizontal. Okay, so the question is going to be, if this object does not move, so if it's in equilibrium, how much friction is acting on the box? All right. So how do we do this? Because we're applying a force at an angle, and we didn't say a number. So let's say I'm pushing down with 100 newtons of force at that 30-degree angle. So how much friction must there be? Well, let's start with a free body diagram. So we've got the box, so the dot represents the box. Now we're pushing down and to the right, so that means if we make a coordinate system here, we're pushing down to the right at 100 newtons, and it's 30 degrees from the horizontal. Okay, now there's other forces acting on this too. You've got the force due to gravity pulling it down, the normal force applying upwards. Okay, and actually, let's be careful here. If you notice, force due to gravity is down. There's also a downward component of this 100 Newton force, which means that combine these two, the normal force must be a lot bigger because the box isn't moving up and down. So that's, if we're going to be careful about our free body diagram, remember, length of the vectors matter. All right, and then what we're trying to find was friction, and so friction would have to point to the left. Now, give yourself some thought as to why that is, because if we're trying to push it right, remember, friction is a resistive force. So if friction's trying to go right, friction must be going left. Hang on, I think I may have said that wrong. If I'm trying to push it to the right, friction must be going left. I didn't say that the first time. That's what I meant to say. So how do we calculate this? Now, if I'm going to balance this out, remember, the only things I can combine are things that are along the same axis. This was the idea of vectors, right? I can't add, for example, I can't combine friction and gravity because they're on different axes. They're in different dimensions. Okay, I can only add things that are along the same line. That means we have a problem here. The 100 Newton vector is not on either axis. It contains both axes. So what we need to do is break it up into both of those components. All right, so let's do that. So let's redraw the free body diagram. But this time I'm going to draw it with forces that are on the x-axis, or on the axes. So normal force is positive y, gravity negative y, and friction was to the left. Now, let's break up this 100 Newton force into the components. Okay, so if it helps, let me draw this somewhere. So I'm going to erase this old diagram, and I want to focus that just on the triangle that it made. Okay, so we had 100 newtons at a 30-degree angle. So if I want to break this into components, how much of it is here on the y-axis? Well, if I look at my triangle, that's opposite to the 30-degree angle, so that would mean I would use sine, so it would be 100 times the sine of 30, which would be 50 newtons. So that means there is an additional 50 newtons pushing down on the box. And then if I look at the horizontal component, since that's adjacent to the angle, this would be 100 cosine 30, which will come out to about 87 newtons. So now I have 87 newtons pointing to the right. Okay, now since this is in equilibrium, it stands to reason that the vertical axes, all those forces should balance, and all the horizontal should balance. But in our problem, we're trying to figure out how much frictional force. So if we look along that axis, that should be easy. 87 newtons plus a negative friction, because it is going in the opposite direction, is equal to 0, because, remember, in equilibrium, the net force has to be 0. So that means, move the friction over, there is 87 newtons of friction acting on this box. And again, all of that came from this idea that in equilibrium, the net force is 0. And that's the part that will screw students up, is we can go through all the ways of setting up forces, but it doesn't answer any specific question. It just tells you how to set it up. Based on what the problem's telling you, you have to make your free body diagram, identify the piece of that diagram you're solving for, and then use any of those numbers to go from there. In the case of equilibrium, it's easy. It all balances out. Okay, so let's try one more example. So let's say in this example, we're just going to go straight with the free body diagram. We're acting on an object, and we're pulling on it with two forces. Let's say we're pulling up with 30 newtons, and we're pulling to the right with 40 newtons. So how much force do we have to pull with, and in what direction, such that the net force is 0? Okay, so obviously right now, if we were pulling on it with just these two forces, it would move at an angle up and to the right. So that means if we want to cancel this, if we want all the forces to balance, there must be a force applied down and to the left so that it does not move. So how do we find out how much force that is? Okay, well, the easy way to say that, or the setup way for this, would be, let's break this up into the components. Right, so this is an unknown force at an unknown angle. But I can say that the x component is what's taking it to the left. And then we can say that there's a y component moving downward. So that changes my whole free body diagram. Okay, so let's redraw that, and using the components of F instead of F itself. So I had 40 newtons to the right. Okay, we had 30 newtons upwards. Now I have the y component moving down and the x component to the left. So what do these components have to equal to balance this thing out? Well, again, it should be kind of obvious. Let's look along the x line. Okay, if these forces are balancing out, that means 40 newtons plus the negative of the x component is equal to 0. So the x component must be 40 newtons. Now, in the y direction, we have 30 newtons positive, because it's the up force, plus a negative y component, and those are canceling. So it follows that the y component must be 30 newtons. Okay, so that means we found a force that has 40 newtons in the x and 30 newtons in the y. So that follows that the final force, this third unknown force, is given as 40 newtons in the x direction and 30 newtons in the y direction. Oh, you may have noticed that that's not exactly true, because the 40 newtons is going left, right? So there's going to obviously be a negative sign on that x component, and there's a negative sign on the j component. Now, typically, it's not going to ask for the components of the force. It's going to want to know, what is the magnitude? So remember, to find magnitude of a vector, we apply Pythagorean theorem. So that's negative 40 newtons plus negative 30 newtons, and each one of these is squared because remember Pythagorean theorem. Okay, and some of you may have noticed that this is just a scaled version of a 3, 4, 5 triangle. So when you go to calculate this out, you're going to get a total magnitude of 50 newtons. And if you want to figure out the direction, we'll do inverse tangent of opposite, which was 30, over the adjacent, which is 40. Okay, and so when you do the inverse of that, we'll find that the angle comes out to 37 degrees. If you notice where it is, it's below the negative x-axis. So now we have magnitude and direction of the overall force needed to put this object, whatever it was, into equilibrium.